Welcome everyone. This is Fred Schenkelberg, and welcome to today's Accendo Reliability webinar. We're going to talk about environmental testing, which is hopefully not a controversial topic of any kind. And yet I've seen it done very, very well and adding a lot of value, and I've seen it done extremely poorly to where it actually is detrimental to the product's performance in the field. And so there's a couple of ways to think about this, and we'll talk about a few of them. And so let me just dive right into it. Now, just before we hit record, I was talking about the way reliability engineers think of reliability is the four-part definition. It's on the first page of the O'Connor and Kleiner's book. It's often within the first few pages of most reliability books is that it's the probability, or a product will function in a designated environment with some probability over a duration. And so, oops. So Joanne, is it not working? I thought I got a check on the sound that it was. So let me pause here for a second and double check that the mic is working. So a couple people are sounding good. All right. So Johan, maybe check well, that's not going to help, but hopefully that works. So all right. Thanks everybody. Sounds like an isolated, hopefully intermittent or temporary problem for Johan. But as I was saying, we often think of reliability the way it's defined in our field is that there's a function in some environment or a product that has a certain set of functions in some environment with probability over durations. And one of the things we want to know is, will it function in a range of different environments, right? That's kind of the genesis or the idea behind environmental testing. But the environment is pretty broad. It's what do we exactly mean by that? And what do we really want to get out of that? So that's one of the areas that I've seen a lot of dismay or ignorance or willful disregard for what are the environmental elements and use elements of our customers' use of our products that really matter, and which ones do we not need to spend much time on. But the idea is that in order for our products to be successful, to not fail, they have to work where the customers use them. And wishing they all work or all of our customers used our products like we use them in our laboratories and on our desktops when we're developing is pretty much folly, as you can imagine. Yet it's that definition that drives a lot of the questions around, well, will it work for our customers where they use it? Now, some people are really good at getting this right and some aren't. And the rhetorical question for you as we get started, do you really know? Are you surprised by where customers use products? And by the types of stresses your product sees and so on? Do you routinely call those customer abuse, or is it that's where they really use it? And maybe we miss that in design. So let's get into it a little bit, and we'll end it with a couple of different ideas about how to go about doing reliability environmental testing in a useful way, and a couple of examples of ways that are not all that terribly useful. Right. When I think of environment in that four-part definition we use, it includes the weather and it includes the usage, and they're related but different. And so we'll get into that a little bit. And one of the things I find is that, hail and rain are just two of many, many factors that deal with the weather. Folks that live in hurricane areas know about high winds and lightning and surge tide or flooding and heavy rains and stuff like that. Others, where I grew up, knew a lot about snow. I didn't have as much snow as upstate New York, say in Buffalo, yet we would routinely get 3, 4, 5 feet of snow in the winter. All of the lakes would be frozen pretty much solid from about Christmas until Easter. So good 3, 4 months some years. It would get to minus 40 degrees without wind chill and Fahrenheit. And that was cold. And it was amazing. I used the unofficial logo or motto for the postal service here in the US that, you know, they would be out delivering the mail in minus 40-degree weather. It was amazing to me that they would deal with that, because it was, then again, it's not that bad because my friends and I would still go ice skating at outside in 40-degree, minus 40-degree temperatures, but not for long. But what I see lots of people do is they use, well, they have to make a decision or they just ignore it. Are you using an average or the absolute maximum or some percentile? And when you do rain testing, say your product is going to be outdoors and needs to withstand various kinds of rain, are you using the heaviest rain you've ever seen, or the heaviest rain ever recorded, or driving rain where there's different wind speeds involved? Um, I saw a video the other day of a storm in the Midwest recently that had, kind of grapefruit size of hailstones. I don't know of anybody that would test their product for that size of a hailstone, yet they do exist. And is that a threat to your product or not? The One of the most interesting questions I got about weather was years ago when I was working at Hewlett Packard, was a factory or a facility in Southern California, uh, was in the area where a lot of low-lying smoke from wildfires was going through their valley. And they had a bunch of servers that had forced air cooling and stuff like that. And they were noticing the smell of smoke in the server room. And so the question was, does smoke cause damage to electronics? And it was pretty easy for us to sort out pretty quickly that yes, it does. It adds a lot of particulate matter that are burned byproducts. That's what smoke is. And a lot of that stuff is really not good for people, much less for electronics, because it tends to be sticky. Think of like a tar almost. And that impedes thermal transfer if you're trying to keep something cool, which these guys were obviously doing. It also is sometimes conductive and or corrosive. So there was a whole bunch of issues with that. And sure enough, the units they kept running because they needed to keep running until they could get replacements, um, tended to fail pretty quickly. And so it really is a problem. But many of us don't think of carpet fiber or dander or just particulates from fabrics when we're thinking of environmental testing. Yet, if it's a household product or even an office space product, those things can really muck up your electronics, especially if they have cooling fans of some sort or another. Yet, it's not on the standard list of things that we do. There's not a lot of Arizona road dust in my house, at least I hope not, but we certainly have pets and they do shed a lot. Speaking of pets, we have critters. I did find a rat once in the back of an inkjet printer. Uh, we found the root cause because it died chewing on a power cable. Um, so it wasn't, I think, what it intended to do, but there it was. And the customer returned it to us as is. Um, so the failure analysis was pretty quick with that, although not a pleasant deal. Yet when I look at products and types of failures that occur for all kinds of different products, I think I've told this story before on one of these webinars, is I was working with a team that was making power meters for, say, like your home, and they were put in the ground. This was typically used in the South, where the frost and freezing ground wasn't a big problem. So the power lines would come into the home buried, and so the meter would be in a chamber along that line underground. And the issue they were really struggling with was that fire ants, and this was mostly in Texas, I believe, were attracted to low voltage electric fields, to electric fields of some sort. And the meter itself was a node for this field being produced because of the way it worked. And these ants would eat through just about everything, uh, all of the polymers and all of the seals and stuff they used for this device. They would eat through that to get closer to the source of this field, and thus destroying the meter, allowing moisture and other things to get in there and cause corrosion and failures. So it's in some industries, these things are known, and or you find out the hard way because your customers complain about it not working where they want to use it. And the yet we keep creating new and wonderful places to put our products that include yet another set of stresses and different kinds of conditions that can take apart our products. Now, we could spend decades looking through and testing for every threat there is, and we'll get to that in a minute, of how to avoid that. Yet firmly believe the first part of knowing if your product is going to work is, one, is it technically possible? Can we even get one of them to work in the lab, which sometimes is a challenge. But then second, what are the threats? What is the range of types of stresses, whether it's high wind or fungus of one sort or another, that could threaten our product's performance? It could degrade it or cause it to fail in one form or another. Now, that may sound like an FMEA, yet we often don't get to the point where the cause of the failure was fire ants, unless you happen to be familiar with it. So being aware of the full range of ways products can fail helps you with the risk assessments and with the design decisions that are occurring. So it's why I'm bringing up these more ones I've learned kind of the hard way over the years, along with my clients. The other one is how it's used. It's the idea is some products, say the servers that are at, say, one of the Google or Amazon or Microsoft server farms, those things run 24/7. And in some of them are, it's set up in such a fashion that, say, power supplies and other likely things to fail are hot swappable, so that they don't lose the performance of those machines even when they're degraded. So they may have redundant power supplies, so you can hot swap out the bad one. There's all kinds of ways that we go about making products work 24/7. And what I found, and I was trying to find the study the other day, that the same vehicle used as a taxi will go 500,000 miles just fine. And it's used 24/7 in some cities, and it's just got shifts of different drivers using it. And as long as they do basic maintenance and use the proper fuels and oil changes and other things like that, the vehicles can run and run and run for a long time, for many, many miles. Yet the same model car used as a home vehicle for a family that maybe does a commute and maybe runs to soccer practice and to the grocery stores and stuff like that are rarely used in comparison to those taxis, and tend to have a whole different set of failure mechanisms from when a product is used quite often or continuously versus one that's used sparingly. And we all can think about that. Is a good number of products that we deal with in manufacture and design and so on have significant periods of downtime. And what's interesting to me is that we often don't focus on all of the ways things can fail when they're not in use. And I use the car as a simple example, as many of us for the internal combustion engine know, that as the oil is not being circulated through the engine, the areas that need that lubrication start dry. And any mechanical engineer knows that's usually not a good thing for wear patterns and so on. But once it gets started, in a few rotations, the oil gets distributed and so on. And yet, every time you start a cold car, it creates much more damage than when you start a warm car. And so the notion is that the just sitting idle allows it to have this unique stress that occurs that cars that are used all the time don't. Now, both vehicles, the taxi and the passenger home vehicle, experience UV degradation of their paints just because they're outside, whether or not they're using. So there's really a couple different classifications of stresses that apply, whether or not you're using the product or if you're using it 24/7 versus not using it very often at all. Now, aircraft have ground types of activities when you're using actual brakes on their wheels to stop before as they get to the gate and so on. But the brakes are of little to no use. They're just being stored going through a thermal cycling cycle when they're in flight. Yet the fuselage has a different set of stresses when it's on the ground versus when it's in the air. So thinking through transport, storage, whether it's used, where it's not used, all of those things, the spark, what is the environment set of stresses that relate to how it could fail in those areas? And that's something to think through before you start setting out what do we need to test is what could go wrong. And ideally, you're doing this very early in the program so that the design team becomes conscious of the dominant stresses that they need to design for, including if it might be enough access to get a rat inside of it. But hopefully your products don't have too much problem with that. Right. So what has surprised you with hit the chat window? What kind of environmental stresses or use stresses that have you seen that maybe we all can increase our awareness to something unique? Unexpected transport conditions. Yeah, Yeshwanth. Yeah, I've seen one where the boxes of personal computers were putting on a cart. I'm not sure what the propulsion was, but it was a wooden cart with wooden spoked and wooden rimmed wheels. So, and going over cobblestone. So I imagine the vibration was not anywhere in our profiles. Bacteria that eat steel. Oh man, that's bad. Ants. Yep. Yeah. No, yeah, I hadn't heard about the steel that eats the bacteria eating steel. I've heard of bacteria breaking down waste to create energy and stuff like that, or to recycle plastics. But yeah, there's it's an amazing world we got out there that can um, help the second law of thermodynamics work in an accelerated way. Good, good. All right. Now, there's a couple of ways people that I've seen in my explorations and assessments of range of vendors and clients and companies that go about doing environmental testing or something that's similar to reliability testing. And one of the best ways by far, with few if no assumptions whatsoever, is to do it in real time. Give it to your customers and or give it to your employees and use the product. What's amazing about it is that it uses all of the combined stresses that the product would see in actual use. Now, of course, this doesn't always work, right? We don't always have the ability to or time to do extensive type of beta testing with our customers. And the hard part is that even though each individual product is seeing all of these different environmental stresses and use stresses as a customer would in real time, if we're only doing this in San Francisco, we're going to see relatively moderate temperatures year round. We're going to see salt fog a little bit, not a whole lot, and environmental conditions and use patterns that are unique just to San Francisco. Now, we have very moderate, I live close to San Francisco, we have very moderate humidity. Now, will your product learn anything if you've passed this beta testing, say, in a moderate humidity area, if part of your desired customer base lives in Houston, Texas, where humidity is anything but moderate? And so getting it out to the right people or the range of people that you want it to get to can be a challenge, and it's expensive and it takes time and for it to work. But how many different places and locations and types of use cases would you really like to explore and understand? Let's say, see on a couple more. Let's see. So Michael's talking about, I think it was the last question, locomotive manufacturer, and they didn't take into account the wide gaps at the ends of rail pieces caused by a lot of shock in service and caused early failure to bearings. Interesting. Yeah, that would do it. Especially when it gets cold, those gaps get bigger and bigger. And I've seen it where when it's hot, those gaps disappear, and now you got a different problem with them bending. Let's see, Jersey's talking about consider a component designed primarily for transmit electrical energy, where the dominant damage mechanism is fatigue caused by thermal cycling. Yep, that happens a lot. With the method of inducing temperature change, electrical cycle self-heating versus ambient temperature, affect the validity or relevance of the test result. Yeah, no, that's an interesting question, and I actually have some experience with it. When I was at Hewlett Packard, the team that I was working with did a lot of thermal cycling, mostly for solder joints. It was when lead-free solder was becoming the norm, becoming imposed on us, basically, but replacing lead solder for all kinds of reasons. And one of the issues that we ran into is that the the slow pace of most thermal chambers, it caused, was trying to replicate the type of ambient thermal cycling from day to night, for example, but what we found is that the self-heating element for most components created a different set of thermal gradients that that not only move the solder joints relative to each other, say in a straight horizontal shear type motion. I'm using my hands here to illustrate this, which isn't helpful for you, but it also would, like potato chip, it would lift the corners or compress the corners of the device itself. So the thermal gradient would cause its own set of stresses within the component that would change its structure. It would move relative to its CTEs, coefficient of thermal expansion, um, and not always in the same direction that we would get if we just put it in a chamber without the self-heating. And so it really depends on how much self-heating you're getting and what kind of distortion those components were seeing. Because if you're not doing self-heating and only using chamber heat, it may not be flexing or moving the parts in the similar fashion that you would get when you're using self-heating to do it. So I'm not sure if I explained that well enough, but the idea is that, yeah, they can really do interesting things to your product depending what the source of heat is. And the best example I've ever seen is that if if you ever seen the production line for electrical circuits or electrical boards, in some facilities, they have somebody checking to see everything's soldered correctly. And they have a soldering iron in their hand and they're ready to touch up any components that are lacking a particular amount of solder or the right shape of it or whatever. But if they take that 400 degrees Celsius tip and touch a ceramic capacitor, that thermal shock will fracture that capacitor. Now, it's not often visible and it'll pass electrical testing most of the time, but it's a latent defect and that capacitor is pretty much out of service going after that. So that's a different kind of thermal loading that may not be an environment we'd always want to get to. Let's see. So the idea, Jersey, is that be very careful about substituting, say, mechanical stresses for thermal stresses if it's strictly a CTE mismatch, or using cheaper, easier to control thermal cycling in a chamber where you're not powering the unit, because it really affects in many cases, the types of movement that creates the wear mechanisms, that creates the fatigue damage. So in most cases, you got to be very careful about how to set those up. And I do know, as you probably do, that doing self-heating in the chamber takes a bit more setup and rigging to make it all work. Yeah. There, and Kenneth, you're right. There's liquid nitrogen cooling chambers that really help with the thermal cycling. And there's even chambers that do such a good job at it. And there's dual chambers where you just move the product from one chamber to the next that can do thermal shock, which I've roughly heard defined as 50 degrees C per minute temperature change. And I think there's some parts in the world where walking out indoors to outdoors would give you that kind of shock. But yeah, again, you got to be pretty careful about how do you translate the application of thermal cycling in one form or another to how it's actually done in your products in the customer's real time. And so the idea of, is it power or internal heating, or is it through ambient heating or some combination of those, is really pay attention to how the stresses change. And good CAD and thermal modeling systems can help us do that. But be very, very conscious that if we use what's available in our lab to cause stresses to occur, we have to be very cognizant that it has to be translated to how it's used in the field. And I mean, I ran into one test. It was for a flexible wristband thing that would monitor health, and it would track your sleeping and number of steps and all kinds of weird stuff. It was a pretty cool little product. But instead of being like a watch with a clasp and all that stuff, it was basically, it would wrap around your wrist by like 1 1/3 time. Think of it as a fancy bracelet where the tails overlapped each other across your one side of your wrist. And to put it on, you could deform it slightly to get it on your wrist. Or there was a handful of different methods that we saw customers using it, that they would put it on their wrist in different ways. And so but they were concerned about how many times can you open and close this to put it on somebody's hand. And the engineer said, before I was involved with the program, said, well, let's use the worst case where they stretch it out almost flat, which takes two hands to do, by the way. And then they created a mechanical device that would take this bracelet type device and flatten it out and then bring it back. And so it would be mechanically extend it, hyperextend it, and then let it relax, and hyperextend it, relax. And figuring that they could accelerate that, the way how often it does that, conscious of not creating internal heating. And they estimated how many times a customer would put this on and off per day and how many years they want it to work. And they said, well, if it can survive the hyper extensions for 2000 cycles, then it's good for 2000 cycles in normal use, which doesn't hyperextend it. And I thought it's a rational logic. But what they missed was the observation of how customers actually put the product on. Vast majority would hook one edge of the device on their wrist and then twist it around the wrist. And it was the twisting motion that caused the most damage, way more damage than the hyperextension did. And so we just had folks, had 10 people volunteer or were volunteered to put this wrist thing on and off and count how many times until it didn't work. And so they would put it on and off, say 100 times, and then they test it to see if it was still working and kept going. Well, it didn't take them very long, and I don't remember the actual numbers, but it was a third as many cycles as the test rig at what we thought were worse conditions would do it. So as part of this real-time approach is that you eliminate this assumption about how do I translate our lab testing or our chamber testing and everything else to actual use. We get real data that way. And if you can wait until it gets to the field and it is sold, then you get real data. If you're monitoring the types of failures and have some way to monitor what's the relevant stresses. Hence the beta testing type approach. So it's from almost every rig that I've ever seen in the lab, it's every step you take away from actual use is another assumption that you're not getting too far away, either bringing on unique failure mechanisms that won't happen in the field or stress it in such a way that it doesn't excite the failure mechanisms that we really need to learn about. And so it can go both ways, but we need to be very, very conscious of that as we set up and create our environmental testing. Standards, my basic message to you is just they're an interesting read. They give us lots of ways to go about doing testing, types of things that other people have thought about as ways to apply various types of stresses. But they are almost always insufficient to really tell you, is it going to help your product learn something about how it fails? And one of the very first expert witness jobs I had was on a Windows that go in homes. And it was a product that was getting sued for whatever reason. And I was asked to take a look at how they qualified the product to have a lifetime of the building type of warranty. And they used a standard in the building industry that said for rain, it has to have certain amount of volume, certain amount of force, and so on. It was basically you go out to your garden, take a sprayer, and oversimplifying this a little bit, but you hook up a garden hose to a spray nozzle and spray the window for half an hour. And then you check for leaks on the inside. That was the test. And then oversimplifying it, obviously, but it was basically a setup where you take a brand new window, you install it in a frame like it would be in a home. And you can imagine that this frame is very specifically built to fit that window. And it's done knowing you're going to go do testing. So it's probably the only window frame they're building that day. Unlike a home builder that's putting in 50 windows and 3 buildings that day and is just ripping through there, putting up the framing and you know, quarter inch here, that, and not square, not this, that, and the other. But it also, what do you think that standard test of build a frame in your warehouse, spray water at it for half an hour, what is it missing that would affect the soundness of a window on a home? Yeah, good as new is not good enough. Excellent. Temperature, yes. Thermal cycling. So the wood moves and the metal frame or polymer frames have a different CTE than the wood. And so yeah, and also missing just the variations in dimensions, the installation practices, and so on. So if you're okay using a perfect window that you know is being built for this testing with a perfect frame that doesn't see any thermal cycling or driving rains or hailstones or whatever stresses that it sees as it degrades over time, but then it's good. You're kind of missing the point of what we're trying to learn here. If you just want to know, is the design able to withstand moisture and rain, that's good, right? But from a quality point of view, I always joke with quality folks is they only have to be good once and we have to do it over some duration. It still has to do that. There's no aging, there's no thermal cycling, there's no wind, there's no shear, there's no anything that occurs to this structure that then eventually led it to fail, usually within the 2 or 3 months when it got installed. And so the idea, and I've seen it over and over and over again, the standard says, do this and pass, you're good. Well, they often skip the good part. Like, good for what? If I do 85-85 for a week, okay, what does that mean? How does that apply to translating it to the way my customer uses it in any meaningful way whatsoever? And the standard's pretty quiet on what that really means, whether it's good or not good, whether it's useful or not. What failure mechanism is it even looking for? So I look at standards, I get ideas from standards, how to apply stresses in various forms. It's sometimes a condition of sale. We have to pass specific standards for our customers to even consider the product. But other than that, I don't think standards help a whole lot when we get to the lab and want to understand the stresses as they're applied to our products. So I say just avoid those. Another approach I've seen is what's called the waterfall approach. And there's variations of this all the time, but let's say you have um, that window idea is that once it's installed and we've set up samples that have different types of dimensionals, things and alignment and manufacturing practices that give us a range of different ways it can be installed. And then we put it in thermal cycling. We give it, say, a year's worth of thermal cycling. And it's basically just ambient. So a big chamber might be sufficient to do that for us. It might take us a while, but we could apply that. What about dust and debris and termites and all the other ones? Well, maybe we're not too worried about that. The warranty's only a year and stuff like that. But let's do the thermal cycling and freeze thaw cycles and then do the water exposure. So set it up in a way that would, if we can't do the spraying inside a thermal chamber, then let's sequence them so that we create the damage so that the failure mechanism can be excited and then we can find it with, say, the water spray testing at the end of it. And I've seen some pretty intricate ones where they have 15 or 20 different tests sequenced in a way that, in part, was what are the most benign to start so that the samples can get further along, but always with this sequencing so that the types of failure mechanisms can damage seals or things like that before we get to the test that then would expose that they existed or not. And it's a decent compromise especially when we have limited samples. And to be honest, we almost always have limited samples. And so the idea is to think through what are the failure mechanisms that are likely to happen. FMEAs and risk assessments and things like that will help us understand what we're looking for. And understanding the failure mechanism allows us to think through the types of stresses that would help us identify those if they occur in our product or not. And so it's not perfect. It's not always going to give us a great accelerated life test that tells us that it will last for 20 years or not. you can design them such that you represent a year's worth of stress or 2 years worth of stress or whatever is appropriate. Yet it gets pretty complicated when you're talking about 10, 15 different types of stresses that occur in random ways in the real life. Very few products get 10 drops in random order onto concrete and then go through thermal cycling and then get sprayed on with water. It's, customers don't do that to our products. Well, some do, I imagine. But the idea is that it's a way for us to expose our limited samples to lots of ways of testing. And the downfall I see is that once you get a good sequence going, it's hard to move off of it because it involves thinking through it again. All right. So what should we do instead? Oh, yeah, here's one I saw. And I asked a vendor once about this. They were making thermal chambers, sort of like a Halt chamber. I said, salt fog is a a big issue for coastal environments and for ships and stuff like that. And ships have salt fog and vibration. But why don't we see salt fog vibration chambers? Why is it we don't do that? And looking at the questions, yeah, Kenneth, you're right. They corrode. They corrode the hammers that create the vibration. It's really hard to create a system that is metal of one form or another that is salt fog resistant. Back to Jersey's part of this is, yeah, you need to understand the impact of sequence, assuming a cumulative damage, right? And that's really starts with understanding the failure mechanism, the ones of interest that you're looking for. So anyway, unfortunately, we um, do not have chambers that do salt fog and vibration at the same time for all kinds of reasons. But salt fog is usually done. Um, there's a town just south of San Francisco that gets, I don't know, like 200 days of the early morning mist off the ocean. And it's a heavy duty salt fog. It's as good or better than any chamber I've ever seen. And so solar panel folks tend to put their products out there to do the salt fog testing. And it doesn't take long to know if you got a problem or not. All right. So how about this for an idea? Let's start with what we know, but more importantly, what we don't know. So part of helping a design team create a reliable product is being aware, like at the start of this presentation, of the range of environmental stresses that our product will be exposed to. And some are going to be pretty benign, and some are going to be, we don't really know how that's going to affect our product. And is it perceived as enough of a risk that we need to run some experiments or do some observations to find out how it does? I'm quite sure the first handheld devices, somebody thought, well, what if somebody drops it? Right? Well, what if somebody drops it? Let's take our prototype and drop it. And if it doesn't pass, it doesn't survive, it gets just crushed into lots of its individual components. Well, we're not there yet. But coupled with that is, well, how often would people drop their products? And it depends on size and handheld devices, how often it's moved, the type of customers and the care they put into it, the price point, all kinds of things go into estimating those kinds of values. But we can start on that without a design even, right? We can start thinking through what are the types of stresses that this product would go after. I often call it a day in the life of the product, and then go through different use cases. How would somebody that uses this every day use it? Say a set of tools in a mechanic shop, or tools in my house that get used maybe once or twice a quarter kinds of stuff. What kind of mechanisms and performance and types of know-how of different kinds of users and so on and so on. You can start thinking about what you know and don't know and sort out how do you get there. So Kenneth, what is the ISTA ship tests, because the standards I've seen on that take kind of a grand average of shock and vibration and things like that they see, um, or types of salt fog and thermal cycling. But it's if you pass that, does that mean that you're good for a container coming across the ocean on a truck and then on a train? Or is it kind of a set criteria? They have drop testing. Yeah, I've seen some of those where it's a huge device and you drop it, 3 feet or 6 feet onto concrete or stuff like that. It can be pretty exciting. It also can be relatively unrelated to the actual environment. There's not many environmental tests I've seen that says, one of the stresses is your product is on a pallet and it has to be moved with a forklift. Do you do any testing to tell if your device or your packaging um, can withstand a strike from the forks of a forklift? We probably don't. So yeah, it's a transit testing, but in different scenarios. But if you really want to know what your product does in transit, is get these little data recorders. They measure vibration, temperature, humidity, all kinds of stuff, and ship it to yourself and record that data. And when I was at HP, the gentleman that lived or was across the hall from me did this on a routine basis. And he would call UPS and say, "Hey, did you change the conveyor height in your facility?" And I think it's in Nashville or somewhere in that area of the world. And they go, "How did you know?" He says, "Well, I monitor this. And it's not a 6 inch drop anymore. It seems to be more like a foot drop." And they were surprised he could tell. I was surprised he could tell. But we used his data to create our own internal criteria for shipping and what kind of stresses they would see. Now, the other part, and the knowns and unknowns for how our product is used and not used, is a lead in to design for reliability primarily. And the parts that we don't know enough information about become candidates for design test, for environmental testing. The other part is risk, what I call the red flags. It's a new vendor, it's a new technology. Well, we had to invent this part of it. All of those kinds of things just kind of go, what do we know about this? What understanding do we have as an organization how this behaves with our customers? Now, if it's from a sister product and they have lots of information, it's not that big of a deal if we know what the differences are. But sometimes it's just brand new. And we just need to ask all kinds of questions about what are the expected failure mechanisms? What are the types of stresses that would degrade or destroy this particular element of our system? And of course, field data. If we've been at this more than a few, cycles, and and this is a big assumption, we get samples back and we do decent failure analysis. And we really understand the environment that it was in and the sequence of events that occurred led to its failure. That's not a given in most field data. Yet, the better that is, the better that information is as we start to consider what's a threat and what's not a threat, what's prone to cause degradation of our products, what's not. So use that data, and it's also a really good reason to get that data to make it really work. Yeah, there's another comment about military tests. I've done just about everything out of the mil. I think it's mil spec or mil handbook 810, except for ballistic testing. Luckily, I've not worked with products that required to be ballistically sound. A parachute to the ground with special platform stillage. It carries out emission. It's a good example of accounting for noise factor, unexpected conditions that affect performance. I bet you they put it into a really big open field without trees or buildings. I think that would ruin their day if the Hummer comes down on a steeple or or a metal fence of some sort or a rock fence. Um, yeah, I always wonder about test conditions that, like, there's one of them for vehicles where it goes over a rutted road or what's it called, a washboard. So it has a certain dimensions and certain hardness of the bumps that are created in a pattern on a road. And I've seen roads much, much worse than that in real life, and I've seen others that are just why is this even a road kinds of things. So we're driving over it. But one of the trade-offs in doing testing to a standard is then you can relate that to what your actual field performance is. And so if we're seeing failures in the field due to vibration, due to rough roads, well, our test is probably not rough enough or long enough to give us the similar failure mechanisms. So we can, by standardizing it, we can uh, learn from our mistakes and improve or make our tests more harsh or whatever. How about we do that beforehand? Don't start with the standard, but then really get to understand the actual environmental conditions and stresses that our customers are expected to use, and then tailor the test to do that. So part of it, the first part is, what do we need to know? What are the questions? What are the key decisions? Is this vendor's product better than this one for our particular application in our environment? Is this attachment sequence for the frame of a window going to withstand the thermal cycling and the various stresses it sees? We need to evaluate those, and we can do that through simulations and mock-up tests and prototyping, but eventually we're going to probably really want to know how it works in the real world. And that brings up, we need to understand what decisions our design team and our management team need to make. And it's, what is it, what information do they need? It's not what tests are we going to run and provide them information. It starts with, what do they need to know? So if we identify these window frames as susceptible to damage due to thermal cycling, and we haven't done that before, and they want to know if this new frame attachment is going to work in this environment, well, then let's propose that the information they need is, does it withstand thermal cycling damage, or installation damage? Let's focus on that versus just spraying water at it. So if the primary decision is this watertight, couple that with our understanding of the failure mechanisms and how it gets there, and then propose the sequence of testing that would replicate the type of sequences that would lead to its failure in the field. As opposed to, oh, we got to make sure it's watertight. Let's use standard ABC and spray some water at it for a few minutes. But the idea is that every single environmental test we do has to have a recipient for that information, not just pass fail, but how did it do? And ideally, we run them to failure with whatever test we do so that we can get, what kind of margin do we have? Can it withstand hurricane force winds for 20, for 2 weeks and do it every year for the next 20 years? We could probably design a test that would help us understand that. Yet, do we need that information? So the idea is, who needs to make decisions? Is this good enough? Is this the right choice? Is this design solid? And then working with them is, what information would be informative to them as they try to make those decisions. I think that's key. It's completely different than what I see in most environmental in testing setups I've seen. They get a sequence of stuff and they just run it over and over for everything. But what do we actually need to know? Yeah, it makes you feel all warm and fuzzy if it passes a whole bunch of environmental tests, but did it really actually add any value? Did it help anybody make a key decision that was the right decision? That we learn enough that we can actually have clear evidence that this is good or not good, and to what degree, which is completely different than passing standard XYZ. And which leads to, do your test selection very, very carefully. It's expensive to do any kind of testing. and it takes time. And to do it well really does take a lot of expertise of understanding failure mechanisms, how the stresses apply, accelerate, or manipulate your products so that they're more or less susceptible to different types of failures, and how all these different stresses act in combination. Now, that's a tall order for any of us to sort out completely for our particular product. The idea, though, by far, the takeaway message for this presentation is you can do a lot of testing, and you can have 15, 20, 30 different environmental tests, and you get one or two samples in each one, and you get 10 minutes for each one of them. I'm exaggerating a bit, but you get the idea that you're not going to learn a whole lot from that style of shotgun approach with very bad aim. The idea is think through what you really need to know. How well do you need to know it? And then all the other constraints we typically have to deal with. But do it as to the best of your ability to get the best information possible to improve our ability to make good decisions across the team. The idea is that if we want to create a good product, say a window, a replacement window or for a home or a new home that will be there for 20 years, really we should be very skeptical, if I can pronounce it right, of a test that says put it in a perfect frame and spray water at it for 30 minutes. Let's actually understand what we're trying to achieve with each and every test sequence we do and select the stresses, the sequencing of stresses, the duration of the stresses, when possible, understand the acceleration factors so that we get really good, solid engineering, scientific data that helps us make good decisions, that this is going to work or it's not going to work over time. And it's not quick and easy. None of our testing should ever be quick and easy. It's got to be meaningful and valuable. And the number one takeaway today, besides that, I thought that was a cool cloud. So yeah, use that image. So is it, maybe this is a hypothetical question at this point, but is it working for your organization? I know we had a few people bring up surprises they had and a few things that, we've been working on, but I got a couple of minutes. So what are your questions? And as I usually do, I'll drop the recording at the top of the hour, but I'll stay online as long as there are questions coming in. So I'm happy to discuss what I can. Carl's made in the questions tab, we put in, real-time standards ensure that systems meet strict timing requirements and deadlines. It's fine. It's replicable. I can put it in a contract and say, you got to do this. If and only, it's only a value if that's the way we're going to actually use the product. If we're going to drive over cobblestone for exactly 3/4 of a mile, and then we're going to do rolling torsional stresses by rolling hills on the road, and then we're going to do washboard for another washboard for a half a mile, and then we're going to drive off a curb, 3 times in a row. Now, if everybody drove exactly like that, that test would be really pretty adequate, but nobody does. And so how do you translate that test to anything useful? And that's where I say you got to really start thinking through this stuff. Now, we don't want to over engineer. We want plenty of robustness, but we don't want to over engineer. I get that. Hence, if you're not tracking your transit stresses, you're in the blind. The standards aren't updated every day for your packaging with your transportation methods. But a relatively inexpensive data recorder that ships out once a week and gets, ships to yourself to another office or to another warehouse someplace and ship right back to you, gives you so much information about what your actual conditions are that why would we ever use a standard? It's our package, our components, our products, in our shipping methods. It's not terribly expensive compared to the amount of information you get out of it. Yeah, Landsmont Saver. And they're gotten better and better and smaller and smaller. Early on, when I first heard about it, we had to be very careful about the mass that the the recorder and its batteries would add to the packaging. And it would, and for smaller products, it would actually significantly change its mass and hence its ability to withstand shipping. So we did a bunch of that stuff. Thanks, Ajit. Glad you made it. Um, but the idea is there's so much we can do that we can get orders of magnitude better information out of those resources we expend doing environmental testing. And so yeah, there's lots of standards out there. And I haven't run into any yet that say, here's how you translate this from a 50 kilogram product to a 100 kilogram product, and whether it's palletized or not, using the yellow truck, which I think was out of business now, but using uh, long haul trucking as opposed to containers or as opposed to air. How do I translate the types of stresses that this standard is applying to my product? And I haven't seen that yet. There's different grades or orientations, but very rarely they say, if you pass this test, it's good forever. I don't think any of them make that claim. There's good reason for that. All right, it's coming up on the end of the hour here. Let's see if I can find my stop recording.